Now let's take the idea of our transfer function and our Laplace transform and use it to model electrical networks. So as we've talked about before, our first step in creating a mathematical model is going to be to apply fundamental physical laws. So if we're talking about circuits, that's going to mean Ohm's law and Kirchhoff's laws. And of course we have other techniques that are a little more sophisticated, but ultimately they're all based on these. So our Ohm's law and our Kirchhoff's laws, which would be our Kirchhoff's current law, KCL, and our Kirchhoff's voltage law, KVL. So what we're going to look at in this class though is we're going to focus on nodal analysis or node voltage analysis. So let's say node voltage analysis. I'm going to link some videos that I have for a previous class that will give you some more details. Ultimately, we're going to work up to sort of a generalized equation, so you don't need to know the process in as much detail as an electrical engineer, so that's particularly for you mechanicals who might not have seen this as much. But if you want to take a look at those videos or some other material, definitely I would encourage you to do that and let me know if you have questions. On the other hand, the textbook also has some material about using mesh current method. So our mesh current analysis is also in the textbook if you're interested in doing that. We're not going to cover it in the lectures, but you can look on pages 40 to 42, 43 to 45, and 48 and 49. So all of those have sort of similar material for our mesh current, but in the lecture we're just going to focus on node voltage. As I mentioned before, these page numbers here are for the 8th edition of the text. As of the time of recording this, the notes posted on Canvas have page numbers for the 7th edition of the text. Okay, so let's take a look at a circuit to kind of get our bearings here. So what we want to do is we want to use nodal analysis, and I'll kind of step through the process a little bit for this first example, to find the transfer function, which is relating the output. In this case, we're defining the output as our inductor current, so this IL of t, to the input, which is our source current, I of t over here on the left. And again, we're going to assume 0 initial conditions. So hopefully you guys remember these components from your ENG 201 class. We have a current source, an inductor, a resistor, and a capacitor. There are, of course, current voltage equations for each of these 3 passive elements. There is a table in the textbook, so that table is on page 39 of the 8th edition, so that could be useful. I'll also put that up in Canvas for everybody as well. One other important thing to point out is that this transfer function is going to depend on where our input and output are defined. So it depends on where output and input are defined. So a lot of times this can seem somewhat arbitrary. Maybe for a certain application, our output would be the voltage across the capacitor instead of our current through the inductor. So just keep that in mind, that just because we have the same circuit doesn't mean it has the same transfer function. We have to make sure that our input and output are defined in the same way. Okay, so let's get into using our node voltage method to analyze this circuit. So in general, when we're analyzing with node voltage, what we want to do is identify our essential nodes. So our essential nodes, just real briefly, N sub E is where we have 3 or more elements connected. So for instance, in this circuit, we're going to have 2 essential nodes. So we have an essential node at the top because we have this element, our current source, our inductor, our resistor, and our capacitor are all connecting up here at the top. So that's 4 elements connecting together. So we can say this whole thing up here is 1 essential node. Same thing for the bottom, because of course we can see those 4 same elements are also connected at the bottom. So in this case, we have 2 essential nodes. So oftentimes I'll just write that N sub E, which is our number of essential nodes, is equal to 2 in this case. So the next thing we want to do is to define a reference a reference node. And so we're not going to worry about how to do that for this class. There are some ways, sometimes where you might want to choose a specific node. In this case, let's just say I want to make it this bottom one, and I indicate it's the reference by putting this arrow. I then can call this one up here on the top my node 1, and I can define some node voltage V1. In this case, notice that the node voltage V1 is the same as this voltage V of t, so I didn't even really have to do that. But again, we're working towards sort of a general process where you don't necessarily need to know step by step what to do in the node voltage method. Okay, and so that's going to come a few videos later. So what we then do is, now that we've got everything defined, we're going to write an equation at each node that's not the reference node. So equation for each non-reference node. And so in this case, because we only have one non-reference node, we're only going to need one equation. And so that's going to be at node 1, which is on the top. And so what we're essentially going to do is we're essentially just applying Kirchhoff's current law. So we're going to say the sum of our current in is equal to the sum of our current out. And so what that looks like, so I've got my currents labeled here. We see that this current source is coming into this node, whereas our other three currents, our IL, our IR, and our IC, are all leaving. So I can say our node 1 equation is then I of t is equal to I of L plus I sub R plus I sub C. Okay, easy enough. So now where things get a little trickier is we're going to go to this table that's on page 39, so that's table 2.3, and we can use our current voltage relationships to sort of play some games and see if we can't find a way to sort of solve for this transfer function. Because remember, ultimately, we're wanting to solve for this transfer function. Okay, so what I'm going to do is I'm going to rewrite this a little bit in terms of the voltages. So I can say my I of t is equal to, and then using my inductor IV equation, I can say that IL by definition is equal to 1 over L integral from 0 to t of V of t times, and so let me actually come back here. So this is V of tau, d tau, just to use a dummy variable. So that's a different way that I could express my inductor current. And again, keep in mind we have 0 initial conditions, so that's why that form's a little simpler than maybe what some of you double E's have seen in other classes. Same idea for our resistor. So again, using that table on page 39, we can say for our resistor, that current I sub R is simply going to be, from Ohm's law, V of t divided by R. And then we have for our capacitor, from that IV equation, we have the current is C times dV dt. Okay, so now what I'm going to do is I'm going to say, well, this V of t, which is the voltage across all three of the elements, all four if we count our current source, because they're all connected in parallel, is equal to our inductor voltage, V sub L of t. Well, we know from that table, table 2.3, that our inductor voltage is equal to L times di dt. So what I can do then is I can say, well, let me come back and take a second look at this integral expression here. So if I consider what that integral expression looks like, I have the integral from 0 to t of V of t, go to my dummy variable V of tau, d tau. And so of course, if I'm taking the integral of a derivative, the two cancel out and I'm just left with L times I sub L of t. And similarly, I can look at this dV dt, keeping in mind that now this V is defined as this, and I can say that my dV dt is equal to L times the second derivative of IL with respect to t. So what I can do now is substitute these in. So I'm going to substitute this and this here and here, and we're going to see what that gives us. So now I have I of t is equal to IL of t, so the 1 over L and the L cancel out when I substituted, plus 1 over R times, we said our V of t is equal to di of t dt right above here. And then finally for that capacitor current, I can now write that as LC times the second derivative of IL with respect to t twice. Okay, I promise we're almost there. What we're going to do next is we're going to take the Laplace transform. So taking the Laplace transform again, remember we've assumed all initial conditions are 0. So this I of t becomes capital I of s. Our I of L becomes capital I sub L of s. And then our R, so we're going to have, and so I've left out an L here, so we should have had an L here as well. So for this term, we have plus L divided by R times S IL of S. So I've used my differentiation property as well as the linearity property. And then I'm going to use those same two properties again for this third term to say we have a constant LC. And from differentiation property, we have S squared times IL of S. And so sometimes it can be useful to not include these of S's because you can get confused and think you're actually multiplying by S. But really that's just kind of personal preference. All right, so now we can sort of rearrange this and we can work our way into finding that transfer function, because remember, ultimately we want to relate our IS, which is our source current, to our IL, which is our inductor current. So that's our input and output respectively. So we can say that our IL of S is multiplied by S squared plus 1 over RC times S plus 1 over LC. And so what I've done is basically just divided through by LC. So I need to divide the other side by LC as well. So I have IS divided by LC. So now finally I can solve for the transfer function. So we get our transfer function g of s, which again, based on how we were told, what we were told the input and output are, is IL of s, our output, divided by our input. And so from the previous line, that's then equal to 1 over LC divided by S squared plus 1 over RC times S plus 1 over LC. So this would be our transfer function and sort of the final answer if we were sort of thinking of this as a problem where we wanted to find that transfer function. Okay, so obviously that was very convoluted, very complicated, particularly through here where I was sort of playing these games with my voltages and currents and using those IV equations, integrals, derivatives. We're not going to have to do that every time is the good news. So what we're going to see in the next couple videos is that this process can be greatly simplified if we just sort of convert the circuit itself to the frequency domain. So greatly simplified if we convert circuit to our frequency domain. And so we're going to see in the next video how to do that, but the basic idea is we're taking the elements themselves, so our inductor, our resistor, our capacitor, and we're going to use something called an impedance and represent that a little differently in the frequency domain.